Okay, so it took a minute to frame this because your general question, where do you get that cosine omega t plus 5 thing? Right? That was your question. So my answer was first use Euler's identity to get the sine and cosine of the sum of two angles. Okay? In terms of the cosine of one angle and the sine of the other. And actually, what I'm doing here doesn't really even address that because this is what you get like when you're doing a phase difference. Okay? So really I'm kind of confusing the context here. But I'm going to go ahead and do this while I'm at it. Okay, so we got this. It doesn't apply here. What you're talking about is like with a phasor in a RLC circuit or something. And phase difference you get there. Is that right?
Well, I was talking about this.
You're talking about this?
Yeah.
Well, let's do this and then we can do that. Yeah, but you got to see how to apply these things, okay? And they come up in many different contexts. So I kind of went to this context, which is what it didn't intend to do, but that's what you wanted me to do anyhow, so we'll do it, okay? So in this context, it's like you have a solution of x double prime equals negative omega x, okay? That could be an RLC, an LC circuit. Could be a simple harmonic oscillator. Could be a physical pendulum or just a regular pendulum, you know, mass in a spring. Okay, see those ideas. Okay, so you want to show that this gives us this general solution. And it's worth working through. Okay, so first of all, A and B are complex numbers because we're in the context of complex solutions, right? So this left-hand side becomes A and okay, we're not using an A in here anymore. I'm going to say A1 plus A2I for A, for a constant A. And e to the I omega t, of course, is cosine of omega t plus I sine of omega t. Then it's going to be plus B1 plus B2I multiplied by cosine of omega t minus I sine of omega t. Okay? It's a cosine of negative omega t, but the cosine's an even function. So cosine of negative omega t is just cosine of omega t. Sine being an odd function, you're going to get the negative there. So that should be clear. So well, this comes out to a bunch of terms. It comes out to, okay, what do we have in the cosine? We have an A1 times a cosine, right, plus B1. Now we want to write the real part of this thing out, then the imaginary part. Okay? So to continue getting the real part, A2I times I sine omega t gives us negative A2 sine omega t, right? And this product gives us plus B2 sine omega t. So we have that's the real part of our solution. The imaginary part is easy enough. It's, you got an A1 times I sine omega t, right? And an A2 times cosine omega t. And we'll just go ahead and put the I here, in the bigger parenthesis. Okay? So we're going to have then A1 sine of omega t plus A2 cosine of omega t, right? But then we're going to have a b1 cosine of omega t and a b2 cosine of omega t. Okay?
We'll have a
A negative b2, a b2 sine of omega t. Let me write it out. b1, sorry, b2I cosine omega t, okay, minus b1 sine omega t. Okay? So b2 minus b1 sine of omega t. Okay? Now I could have collected the a1 and the negative b1 on the sine, the a2 and the b2 on the cosine, right? Maybe I should have done that, but anyhow, this is going to end up equaling just trying to see it all. Okay. If I put all this together, I've got a multiple of the cosine added to a multiple of the sine, right? Okay. If I match that up with what I see here, okay, the cosine of omega t and sine of omega t have the same argument. These things, we have different multiples. Okay, well, let's back up a minute. Okay, rather than try to see it in here, let's get the other side of the coin on these expressions, okay? Because I'm trying to put this together and see that. I'm having trouble seeing it because I haven't thought about it in a while. Okay, so let's back up a minute.